thank you for the introduction, Elvin, and hello, everyone. Thank you for being here. So, well, yes, essentially, as Elvin said, I am going to be talking mostly about some ongoing work about learning the the topology of DAGs. Actually, this is a work that I started during one visit to Rochester University. So, of course, the first thing to do is give thanks to my great collaborators with this work, Gonzalo and Saman. Okay. And to begin with, I just want to give a high-level image of what's this problem about, okay? Consider that we have observations from a set of random variables. These random variables, of course, are connected. They depend among each other, right? But we don't know this dependency. What we do know is that the dependency has a particular structure, and in particular is that that structure is given by a graph which has no cycles and directed edges. Okay, so essentially the underlying structure, it can be modeled as a DAG. Then, of course, what we are going to, our task here is just use the observations that we have to learn the underlying structure of the data. That is learning the DAG. Okay, that's the whole level, the high level idea. Now, maybe a pertinent question to start with is why do we care about DAGs at all? Here the straightforward answer is, okay, we can actually find DAGs in many different applications within machine learning. To me, maybe the most interesting part is its connection to causality, as Elvin was mentioning. Whenever we have some causal relation between data, that can always be modeled as a DAG, as we can see, for example, in this image over here. Of course, imagine that we actually know that some variables have some causal relationships. We could always try to use that causal information to inform any ML algorithm down the line. However, we need to be cautious here, okay? Why? Because it's true that causality can always be explained as a DAG, but the converse is not true. I can have a DAG, but that DAG does not necessarily account for a causal structure, okay? So just to be clear here, we are doing DAG learning, not causal inference. These two things are related, but they are not exactly the same. In any case, beyond causality, we can also think about some examples where we are going to be finding DAGs, for example, in Bayesian networks, or even if we want to automatically optimize how to connect different layers on a neural network, that actually is going to also have the structure of a DAG, okay? Now, moving on to put this a little bit in context, DAG learning is actually a subproblem of a more general framework, which is graph learning. In graph learning, the overall idea is very similar to what I described at the beginning. Essentially, we have access to observations on some nodes, right? We are measuring some signals, and our goal is to use these observations to learn the underlying topology, the structure of the graph. As you can imagine, this is going to be in general an ill-posed problem, and we need to make some assumptions. In particular, we typically are going to assume some model. The model is going to relate the observations we have with the topology of the graph that we are looking for, and also we like to impose some structure. Typically, this amounts to imposing sparsity on the graph. Now, it is also well known in the literature that whenever we want to learn a graph with directed edges, this introduces some additional difficulties, right? And in this particular case, keep in mind that we are going beyond directionality. What we want, remember, is to find a DAG that is a graph directed with no cycles. And for that, essentially, we are going to find two main challenges, right? The first one, which is the main focus of this talk, imposing a cyclicity is difficult in general. If you can think about the general problem, imposing a cyclicity means that I have to pick a subset of edges because there are edges that are going to be in conflict, such that if some edges are activated and others are also activated, I get a cycle. So that's combinatorial in nature. So overall, hard to impose. And then this is not that much related to this talk, but it's also important to keep in mind. In many situations, there are more than one DAG that can explain the distribution of your data. So the overall problem might not even be identifiable, okay? Now, within this setting, with these challenges in mind, what is the aim of this work? Well, what we want is try to answer to the following question. Can we impose some additional structure into the DAG learning problem to make it easier, to make it more tractable, okay? The answer is going to be positive, fortunately. But to get there, there is the roadmap ahead of us. So I will begin with some background on DAG learning. This is going to be a bit long, like it's not only going to be an introduction, but if you are not that much familiar with the DAG learning part, I think you might find some interesting results here. Also, these are well known. This is not our contribution, but I think it might be interesting. Then I will present our particular framework where, as you see over there, the additional structure we are going to impose, it's non-negativity on the matrices. That is going to help us way more than we could expect it. And we see that on some numerical evaluation. And finally, of course, I will close the presentation with some concluding remarks. Okay. So with this plan ahead of us, let me start by introducing some notation. Of course, we have a DAG that is essentially a set of nodes and a set of edges. Associated with the DAG, we have our adjacency matrix, which we are calling W. The support of this matrix, it's only capturing the structure of the DAG. What that means is if I have an entry that is done different than 0, for example, the entry 1, 4 is different than 0, that means that there is an edge that is direct. There is an edge from node 1 to node 4, okay? The important thing to keep in mind when working with DAGs is that the set of nodes is actually a partially ordered set. And what this means is that I can always find a particular order. I can always permute rows and columns of my adjacency matrix to make it upper triangular, okay? And this will be handy in the following slides. Then, of course, to learn the graph, we need some signals. A graph signal is just defined as a vector where the entries of the vector are associated to the values of the nodes of the graph. Now, when we are working with DAG, typically what we are implicitly assuming is that my DAG is actually encoding the conditional dependencies of the data. What this means is essentially if I want to focus on the signal value at a particular node, say node I, typically I can express that signal based solely on the parents of that node. Okay. Now, along these lines, as I was mentioning, to learn a graph, to learn a DAG in this case, we typically need to assume a model. There are different options we could consider. Typically, when working with DAGs, the most popular one, I would argue, is using a linear structural equation model. Essentially, this model is given by this equation, and what it's saying is very much aligned with my previous comment, right? Essentially, what this model tells us is the signal value at a particular node I is going to be given by a linear combination of the parents of my node plus some exogenous noise. It's some noise. The important thing is that this noise has to be sampled from a distribution with a covariance being a diagonal matrix, okay? And well, of course, we can read it more compactly in diagonal form. Now, regarding the identifiability, and this is the only part of the presentation where this is going to appear, but it is also well known that for this type of model to be identifiable, for there to be a single DAG explaining this data, we either need these random variables to be or non-Gaussian, or if they are Gaussian, they have to be homoscedastic, okay? Well, second, homoscedastic. This thing over here. What means do you mean? The variance needs to be the same for all the nodes. It can also be heteroscedastic. You can have different values, but for that, at least, you need to know the covariance up to some scalar ambiguity. Okay? Yes, of course, by the way, feel free to interrupt me anytime you have any questions. Since we are not a lot of people, that's one advantage. So, moving on then with this notation to the problem statement. Yes, as I was saying, essentially, we just have some set of observations, right? Some data that is collected in our matrix. For our problem, we are assuming that it follows from a structural equation model, but to be honest, we could assume all the different models as well. Our goal then is to learn an adjacency matrix, and we are going to do that by solving an optimization problem. The optimization problem is something like this, which essentially have two main terms, I would argue. The first term is just some function f. This is our score function. This is essentially a function that is going to capture the relation that we are assuming between the DAG and the signals, right? And then we also have this constraint over here, which essentially it's implying that the matrix W that I am estimating has to be the adjacency matrix of a DAG, okay? As I mentioned, of course, well, learning my DAG only from the observations, only from the data, it's well known to be a very difficult task. And imposing the cyclicity constraint, it's hard, it's difficult. As I mentioned, it's actually a combinatorial problem, right? Now, traditional methods, the way that we have been dealing with this in traditional methods is mainly based on discrete optimization. That is, okay, I do some combinatorial search. Well, I define the score functions based on either likelihood or Bayesian score functions, and I do combinatorial search over the space of DAGs and pick the one with a highest score, okay? Well, or the minimum if we are minimizing, okay? Then, of course, the issue is that the space of DAGs is well known to be super exponential of the number of nodes. That means that it's huge. So all these methods face scalability issues. They typically resort to some greedy search approaches, but even these greedy approaches still are facing scalability issues. Like they cannot handle very large DAGs. Now, in this sense, keeping on with the related literature, there has been some more recent progress with order-based methods. Now, remember that we are dealing with DAGs, and what this means is if I were to know the actual order of my nodes, right, essentially, I can have that my adjacency matrix is upper triangular, and then of course, imposing that W, it's a DAG, that's complicated, but working with a constraint that says W is upper triangular, that's easy, right? Therefore, there are many methods that are precisely trying to do this. Instead of working with W being a DAG, they try to say, okay, W, it's a matrix such that it's a permutation of an strictly upper triangular matrix, okay? What they are doing then essentially is trying to find the causal order of the nodes. They are trying to find this permutation. So this implies some progress because, well, essentially now we can look for we can exactly get DAGs in an end-to-end fashion with differentiable methods, which is also what we are going to be seeing in the next slide. But there are different methods. We can either try to learn the permutations. There are also variable optimization techniques, a bunch of different methods. The main issue with these particular approaches is that recovering the order, as you might imagine, it's also not easy. When you have binary edges, it's a bit easier, right? Because essentially the variance of your data depends on the number of jumps you are doing. But when you have weights, it becomes more tricky. Let's say it's more difficult. Yes?
No problem that, for example, now you can switch 2 and 3, right? Without, so basically you have 2 disconnected optimal points. Is that also an issue, or can you move around it?
You mean for this being differentiable, or?
Yeah, so in general, these methods that recover such an order, right?
Mm-hmm.
It's an issue that there exist multiple optimal points that are kind of disconnected from each other. Instead that it's not a continuous problem, right?
It's not a continuous problem, but sorry, I was hitting this by mistake. As far as I know, like I'm not fully aware of all the details, but as far as I know, they typically resort to manifold optimization and things like that. So they do something close to being differentiable, to finding the permutations. So yes, and in particular because yes.
So that's clear.
That wouldn't be a problem in principle, right? Because you don't care that much about the order, you get about getting an upper triangular matrix. Then of course, if you will have another node here, right? Those two are on the same level, you could be swapping the 2 rows, but you wouldn't care that much about that. Okay.
Do we need certain tricks to make it differentiable over this permutation?
Yes, about that tricks to be yes. As I said, I feel they are mostly based on finding like manifold optimization, but I'm not aware of all the details. In any case, now we get to one of the main focus of this talk, right? Which are continuous cyclicity functions. So some years ago now, these papers, the paper known as node tiers, essentially proposed a new type of functions with some interesting property. This is the function H, which is supposed to be applied to our matrices, our adjacency matrix. The key thing about this is that they saw that they can design these matrices such that the zero level set of the matrices correspond exactly to the set of DAGs. Put differently, if I find some W such that this function is 0, that means necessarily that my W is the adjacency matrix of a DAG, okay? And this is great because now we have something that is fully differentiable, unlike in the previous case where we might have some heuristic, okay? Now, to see a little bit at high level how does all of this work, essentially, well, the cyclicity function proposed in this paper has this shape over here, right? It's just the trace of some exponential. I want to call your attention upon this particular term. We need this is the entry-wise product, okay? This is going to be an isolated on, as we will be explaining, but the overall idea is as follows. We can play a little bit with exponential matrix to get this series, right? And then, of course, we have powers of W. Assume for now that W is a positive matrix. which can be because essentially we have something that is entry-wise squared, right? Now, it is well known, of course, the kth power of the adjacency matrix has information about the k-hop neighborhood, right? Therefore, because we have this trace, if we look at the diagonal entries of W, what we have is information about the cycles of length k. So if we look at this with this small example, right, we can clearly see we have cycles of length 3. Looking at the different terms, we have the 0 power is the identity, the first power would be accounting for self-loop, second power cycles of size 2, of course we don't have any, but then on the third power, all of the sudden, we have on the diagonal our 3 different cycles, okay? So essentially, with this small example, the only thing I want to convey is that the reason why this is working is that for this trace to be exactly 0, right, because we are removing the elements from the identity, we need a matrix we have zeros on the diagonal for every power, which means we have a graph with no cycles. Okay, this is the high-level idea. And now, this is actually a huge breakthrough in the area of DAG learning. Why? Remember that we started with a problem that was combinatorial in nature. We had no idea about how to move on this space easily. But now, all of a sudden, we can reparameterize, we can reformulate this problem, as we have it here, still over square function, but now our constraint is that this function has to be 0. And this is great, because this function is non-convex. Sure, it has some issue, landscape is not very amenable, but now we can just run gradient descent. And at least we know how to move towards our space of DAGs, which is his progress. And again, this is just an overview, let's say, but to me, this is one of the key takeaways of the talk. If you're not familiar with DAGs, at least I would like you to remember that nowadays it's relatively easier, more amenable to try to learn the structure of DAGs. And that's thanks to this particular type of constraints, okay? Now, of course, when there is a huge breakthrough, there are a lot of follow-up works. That means there are way more acyclicity functions than the one I just showed you. I am, of course, not going to be listing them all, but at least keep in mind, I want to also call your attention upon the DAG map function, essentially because this is the state of the art. It has some better numerical properties, right? As you see, okay, it's only based on the log depth. That's maybe the only important thing. Also, it's including this entry-wise product. This is a constant almost, maybe not all, but most of current acyclicity functions, okay? And well, so far I just described why all of these acyclicity functions are so nice and why we like them. Then, of course, they have also some limitations, right? If not, I wouldn't be presenting this work here. The main limitation, essentially, it's stemming from this entry-wise product. Keep in mind that just as an intuitive level, we have the entry-wise product, which is non-convex. And that is compound with a different function, which is also non-convex, okay? So essentially, the landscape is going to be nasty. It's not going to be very amenable. But to get more to the point, the main issue appears when we look at the stationary points of this constraint. It is easy to see, in fact, that every DAG is a stationary point of most of these particular acyclicity functions. We can look at the gradient of the no TS function, for example, is just given by this expression. And remember, as I told you before, because I'm working with DAGs, W always can be expressed as a strictly upper triangular matrix. That means this term over here is upper triangular, but this term over here is going to be strictly lower triangular. So the product, whenever W is a DAG, it's always going to be 0, right? Essentially what I was claiming, whenever I have a DAG, any particular DAG, is going to be a stationary point of my constraint. Okay, why is this an issue? Why do we care about that? To answer this, we need to look into the KKT conditions. Essentially, if I want a W to be my optimum, right, it needs to satisfy the following expression. It has to be a stationary point of the Lagrangian, essentially, where we have the gradient of the square function and the gradient of the acyclicity function. But not as I told you, right, but for any W to be the optimal solution, it also needs to be feasible, right? That means it needs to be a DAG. But as I already told you, if W is a DAG, saying is that the DAG also needs to be a stationary point of this function f. And this is an issue. Why it is an issue? Imagine that f is convex, for example. If f is convex, it has a single stationary point. Well, strongly convex, but let's say it has some stationary points. The thing is that we should be able to get to the minimizer, to the DAG structure, without imposing the cyclicity at all. So why do we need this, right? There is an issue. Of course, in practice, what is going to happen this is not going to be holding in practice, in the sense that we are not going to be getting this W to be exactly a DAG. And this is exactly why all these methods find some instability. They need to resort to very particular heuristic approaches to do the minimization and such. So there are some tricks involved. But well, the main takeaway here is, again, this is because of the Hadamard product, and the DAG being a stationary point of the cyclicity function is an issue, okay? And this is what we want to address, and now I can finally start introducing our idea, which, by the way, it's a very simple idea, okay? What we want is to get rid of this entry-wise of this Hadamard product. To do this, okay, we just decide, okay, this is mainly to have a matrix that is non-negative, so we are just going to assume additional structure. What happens if my matrix is non-negative? Is I only have non-negative edges. The first step there is to try and show that we can use an cyclicity function that doesn't involve this Hadamard product and still incorporates this cyclicity. That's precisely what we are doing here, right? Essentially, what we are claiming is, okay, for any non-negative matrix, the spectral radius needs to be bounded. This is the same as in DAGMA. We have the following constraint, which, if you might have noticed, this is exactly the same constraint as the one that there was in DAGMA, with the only difference that we got rid of the entry-wise product, which is exactly what we wanted, okay? And of course, this is going to be 0 if and only if W is the adjacency of a DAG. Now, the proof is actually fairly easy, it's not super complicated, but the whole idea is as follows. I can play again a little bit with the log determinant, and I arrive to this series over here, right? Once again, what I have is the trace of different powers of W. Therefore, for this term to be 0, what I need is, again, is that W has no loops, has zeros on the diagonal for every power of k. Also, I didn't call on your attention before, but this is divided by a factor of k. With no tiers, for example, it was divided by a factorial of k. That means that it's hard to impose a cyclicity for very long cycles. In this sense, this type of function is behaving a bit better numerically. That's a property for DAGMA. That's why it's a state of the art, okay? Okay, this is how the proposition works. Moving on, essentially, I was arguing that DAGs being stationary points of the cyclicity function was an issue. It's very easy to check now that this is no longer the case. We take the gradient of our function is given by this, and now, of course, this is just going to be a triangular matrix if W is a DAG. So not any DAGs are no longer stationary points of our function. So first mission accomplished, let's say. Just a minor remark, we are focusing during the whole work on the log determinant acyclicity, but that mostly because it behaves better. This idea of imposing acyclicity and getting rid of the Hadamard product is something you can apply to almost every acyclicity function, okay? For example, with no tiers, we also have some examples. So moving on, now we are actually able of imposing acyclicity without this Hadamard product. The next step is, of course, formulating the problem. The optimization problem is more or less straightforward, at least the objective function. Essentially, we have our score function is just a fidelity term that is accounting for the structural equation model plus some sparsity. Of course, because we know W is positive, we are just dropping the absolute value, okay? And then the main points of this work, the two constraints. W needs to be entry-wise non-negative, and also, of course, this constraint needs to be exaltly satisfied. We need this to be 0 for claiming that W is a DAG. Now, our hypothesis and what we are going to be observing in the experiment is that essentially because this function is easier now, the optimization landscape of this problem should be more amenable somehow. And of course, this is going to be leading to better results, okay? But this is not for free, and this is the other thing that is important to notice. We have to pay a price, which is the price. We can no longer learn any negative connections. If you have some setting and you suspect your two variables have negative dependencies, you cannot apply this because it's not going to work, okay? Of course, that's the trade-off. If you're willing to pay that, results are going to be considerably better, okay?
There that the spectral radius is less than 1.
Totally correct. I forgot. You should also include here that the spectral radius is always smaller than 1, sure. If you are using the log det, if you are using, for example, one based on no tiers, you don't need it, but yes.
The value of S then important there?
In practice, not much. With this DAGMA, for example, it is important they have this scheduling to decrease it progressively because smaller s is reducing your feasible size, right? Your feasible set. For hours in practice, I just set S to 1 and it's working fine. So not very critical.
My question was assuming that was.
Yes. Yes. Okay. So then just how to follow. Okay. As I'm saying, right, the key thing is for us to guarantee that this constraint is satisfied. So to be able to do this, at least in theory, what we want is just to try to employ some method that it's tailored for constraint optimization with some nice convergence guarantees. For that, essentially, we're going to be using the method of multipliers. And again, why should this work? Our hypothesis is one again that this is going to work because of our more amenable acyclicity function, okay? Because some other works were trying also method multipliers and they have some numerical issues. That's one of the initial approaches in Node.js. Okay, so what's the method of multipliers? I won't enter into a lot of details, but essentially it's an iterative method that is based on the augmented Lagrangian. The augmented Lagrangian is essentially this function over here. I have the objective function, which is our score function, right? I have a Lagrange multiplier times my acyclicity constraint. That's exactly the constraint violation. And then I also have the constraint violation, but squared to penalize last deviation. Now, this is an iterative approach, which means that at each iteration, we need to follow the 3 following steps, okay? Essentially, the more computationally demanding one is the step 1, where essentially we need to find the minimum of the augmented Lagrangian. We are addressing this part. We try different strategies. Essentially, using accelerated projected gradient descent is working fine. The computational complexity is the number of nodes to the power of 3. So overall, it's not bad, okay? It's not the most efficient thing you are going to be seeing, but it's working relatively fast. The second step involves augmenting the Lagrange multiplier. This is very straightforward. It's just some dual ascent step. And finally, we have to update the penalty parameter. Here, essentially, we have some rules, but the overall idea is that penalty is going to be increased whenever the violation of my constraints has not decreased enough. And typically, for the theory, what you need is to this thing to go to infinity for a large number of iterations, and that is going to guarantee that the constraint is satisfied. Now, here is where we observe some interesting behavior. Now, I was trying to convince you that we are using the method of multipliers because we want some guarantees of recovering the constraint solution, right? However, this is not going to be the case. Why? For the method of multipliers to converge to the solution of the original constraint problem, what you need is to be able to find the minimizer of this step. But remember that our acyclicity convex, sure, it behaves better, but it's still non-convex. Therefore, this term over here, it's also not going to be convex. So in principle, we have no guarantees of recovering the solution to the constraint original problem. However, what we are observing in practice is that it's not only that we are recovering a DAG, okay? It's that the DAG we are recovering typically, it's the ground truth DAG, okay? So this, again, an important disclaimer, but an important takeaway. The takeaway is, all what I am telling here is to say, if you are willing to impose additional structure, results are going to be way better. You are actually recovering the ground truth. But be aware, again, we still cannot prove that, okay? That's the part of the ongoing work we are currently working on. But this will be very much clear in the numerical experiments, I hope. And now, actually, before moving to the numerical evaluation, this is, again, a minor remark and some additional examples, okay? Keep in mind that our approach, essentially, is I am going to impose additional structure. That means an additional constraint. And then, thanks to that, I am designing a different acyclicity function. But that, of course, can be applied to a wide range of settings, right? We are not constrained to the particular score function we are using here. An example is the work that Gonzalo introduces, this collide method, where the overall idea is you learn jointly the DAG structure and the covariance of the noise. Why this is important? Well, if you remember, I told you when data is Gaussian, you need the noise to be almost sedastic, right? If it's heterosedastic, you can still recover the true DAG if you know the covariance matrix. And indeed, Collide seems to be doing this Collide seems to be doing a pretty good job here because indeed it's getting something that is close to something that is very close to the true DAG. Of course, I don't have results for this, but essentially, when we impose our additional constraint, we are getting something that it's also the true DAG in many synthetic experiments. So it's also looking good in that direction. Now, out this, I will add this also some experiment. The other setting is, okay, consider that now we are not using a structural equation model setting, but instead we have some time series now, and that time series can be modeled as a structural vector autoregressive model. So very related to SEM, but not exactly the same. What this means is, okay, the goal still is that I want to be able to learn some potentially causal relationships between my variables. So for that, I have some instantaneous time dependencies that still has to be a DAG. So this will be my old matrix W, and here I need to impose a cyclicity. But in addition to that, I can also account for temporal dependencies, right? As we see with the dashed lines. That's essentially what this method is telling me, right? We have the DAG explaining my data. That's the same part of the model, and this is just the part of previous time steps. Well, I don't have all the details, but essentially now it's easy to define a different score function, just accounting for this particular model. Of course, you need to learn W and A jointly, but then you can apply non-negativity over W, apply of a score function, and follow not exactly the same, but a similar method of multipliers. Just the minimization of the Lagrangian needs a bit more tedious because you need to do alternating descent. But overall, this is also converging well into the resolution that we'll observe it. Yes?
Between W and A?
No, they can be, actually in the experiments, they are completely different. I mean, yes, this is just realization of random errors any graphs. If there were a relation, you could incorporate it in the problem, that's for sure. Okay, so now, as I said, this is more a remark, okay? Let me move on to some numerical experiments now. And we are going to be starting with some synthetic data. Now, we have some, of course, non-negative Erdős-Rényi graphs. We are using 100 node. They are pretty sparse, as you can see. They only have average degree of 4. And we are following the structural equation model. Now, in the figure, what I'm showing is the normalized error, which is defined, as you see over here, right? Normalized square Frobenius error, as the number of samples increases. And here there are two main things that I want to mention. First, if we focus on all these lines above, these are essentially the different acyclicity functions involving the Hadamard product. And the first message is that these are already working well. I mean, if you look at the error, essentially we have what? Somewhere between 3 and 7% of error, which is a reasonable performance. However, it doesn't matter how many more samples I have, they seem to be reaching a plateau. The performance stops improving. In contrast, if we look at the blue line, which is our log determinant acyclicity function with the non-negativity constraint, what we are observing, oh, sorry, I don't know what that is. No. Thank you. Oh, it's tactile. Oh, sorry. In any case, what we observe in our case, as the number of samples goes to infinity, the error goes to 0. And also notice that the standard deviation is very small. This is what I was saying. It suggests that at least when NAS data is given, we can indeed find the ground truth DAG, okay? Which, again, to me, it's very appealing because remember, we started from a problem that was NP-hard in the beginning. We need to move from a combinatorial space, which is unclear how to do that. Then we move with this acyclicity function to something that, okay, still non-convex, but you can do gradient descent. And as I said, getting a good performance. And now, apparently, empirically at least, okay, this seems to be converging to the ground truth, which, again, to me, very exciting. Okay, the next synthetic case, just similar idea, but now we have a signal from a structural vector autoregressive model. And now what I'm showing is the F-score. This captures how well the support of the DAG is estimated. 1 is the best we can do. And as the number of nodes increases. Here again, two messages. The first message, both methods, ours in blue and the alternative with other cyclicity functions, are working with up to thousands of nodes, which is good. And it's good, I mean, it's scalable, okay? These are not huge graphs, but you can do the job. And this doesn't take a crazy long time either to run. I don't remember the detail, but it's reasonable. So these methods scale well, okay? And that's thanks to the continuous optimization, to the continuous cyclicity constraint. Of course, then, if I focus on our method, what we observe is that we are consistently getting a F-score that it's very close to 1. Again, this is supporting this idea that we can indeed recover the structure of the true graph. And of course, if we do a better job at estimating W, that's helping us in estimating the matrix A, the time lag dependencies. Okay, and finally, just to close the presentation, some numerical experiment with real data. Here we have the DAG from the SACS datasets. This is like the benchmark for that, for DAGs. Essentially, it has 11 nodes, 17 edges, and around 900 observations. The DAG essentially is like validated by the community, so we can more or less confidently state that this is the ground truth DAG. And here I have the estimated DAG with our method and with DAG. The first disclaimer, as you can see, results are not great. Okay, we have 17 edges. In the best of the cases, we have a structural Hamming distance of 10. The structural Hamming distance essentially means how many entries of my matrix I need to change to get the true one. So essentially, this is telling me you have 17 edges and you need to change 10 to recover the true one. Not great, okay? But at least this also gives an optimistic message, because on the right we have Dagma. And remember, this is state of the art. And they are getting a 15 structural Hamming distance. At least what it seems, we are doing way better. And this is not a matter, okay, this is the way you solve this. No, but it's pointing in the right direction. It clearly seems to suggest that accounting for this additional structure, trying to use this easier, more amenable cyclicity constraint, is helping. And of course, it also validates the fact that there are data sets where maybe you don't care about having positive connections. Maybe that's all you need, okay? And that's where this type of methods can actually shine. So with this, I can actually move to the concluding remarks. So I've been talking about DAGs for a while. Remember, why do I like DAGs? They can have a relation with causal inference, and in general, they can always model conditional independencies, right? The main two takeaways. First of all, there has been a huge breakthrough thanks to these continuous cyclicity constraints, which allow us to essentially solve the DAG learning problem using gradient descent. Again, that's great because it's scalable, okay? And the second main takeaway, if we are willing to impose additional structure, this non-negativity on our connections, we can get a problem that is way more tractable. Why? The hypothesis is that it's because we are getting rid of this entry-wise product on the cyclicity, and that's making our optimization landscape easier. And then, of course, we are observing at least empirically convergence to ground truth DAG, and this is somewhat a flexible strategy, because in the end, this is just a type of a cyclicity function you can incorporate in different problems, or different problems with different, you can play with different score functions. And of course, the ongoing and future work, as I think I've already mentioned several times, it's great that we empirically observe convergence to the global minimum, right? Or to the true DAG. Now we have to characterize that. And that's proving difficult, but that's what we are working with right now. And this concludes my presentation. Thank you all for listening. If you have any questions, I'll be happy to answer them.